My apologies for the archaic use of English. This word divers is one I very often use. It really just means various distinct ways of describing things. What I'm going to be looking at in this lecture are the number of different mechanisms that have been developed for describing the form of complex numbers. There are several such methods available. None is superior to another, but sometimes one particular representation form is much more convenient depending on the application. It's probably not politically correct to quote Kipling anymore. I don't really care. I like Kipling. And this is one quote from a poem of his, which basically captures the fact that different forms of representation are just different forms. There's no superiority of one method to another. There are 69 ways of constructing tribal lays, and every single one of them is right. So let me just review some of the background we had previously. So to start off with, we met this approach to describing objects which I am going to be referring to subsequently as complex numbers. Basic form of a complex number, we have two real numbers, one which we refer to as the real part, this part A, and one which we refer to as the imaginary part, this real number B. Typically, we'll write a general complex number as this algebraic structure, A plus I multiplied by B. So, this typical form that we have here on the slide. I introduced this object referred to as a complex plane. So this is where we take our standard two-dimensional axes, but instead of looking at the horizontal and vertical axes as standard x and y coordinates, we think of the horizontal axis as describing the real part and the vertical axis as describing the imaginary part. And this view of the complex plane, this gives us another way by which we can interpret a complex number. It's just as a coordinate in the complex plane. So these are two quite basic methods for thinking of complex numbers. We're not limited to those two forms only. So what I'm going to do in this lecture is look at some of the alternative methods that have been produced. So to start off with, we have this method which describes the complex number as a 2 by 2 matrix. So we take our arbitrary standard form for a complex number, is this addition. And if we want to write that as a matrix, we can do so in this way here. We have the real part of the complex number written down the leading diagonal, and the imaginary part written across the other diagonal, but we substitute minus b for in the first row rather than b. And if we take that form, it turns out that the basic operations we have on complex numbers can just be thought of in terms of manipulating 2 by 2 matrices. So the addition of two complex numbers, that's exactly the same as the addition of two matrices. If we look at the conjugate of a complex number, that's exactly the same as taking the matrix form and computing its transpose, the operation where we substitute for the first row the first column, where we substitute for the second row the second column. If we want to compute the size of a complex number, that corresponds to this object which I referred to as the determinant of the matrix. And finally, for multiplication is of two complex numbers just corresponds to multiplication of the corresponding matrix forms. We have another diagrammatic method for describing complex numbers, which is referred to as an Argand diagram. So here what we do, we think of our complex number, the real part and the imaginary part, as being a vector in the two-dimensional plane. So the size of the complex number is simply the size of the vector. And we think of the vector as being drawn from the origin up to the point in the complex plane describing the number. And that representation, well, it has a few advantages. If we take an arbitrary complex number again, this issue of what do we mean by the square root of -1, well, that doesn't arise because all we are doing is we are expressing properties of complex numbers simply in terms of operations on standard two vectors, two-dimensional real vectors. The addition of any two complex numbers, well, all that's doing is mimicking the process of vector addition. Our notion for conjugate, we now have a geometrical interpretation of it. That is just the process of reflecting the corresponding vector in the real axis, in the horizontal axis. This notion of modulus, this notion of size, well, that's just our standard notion of vector size. The use of Argand diagrams, or this geometric form, it has some disadvantages. So these operations of multiplying and dividing complex numbers, they don't seem to have a natural geometric interpretation. The Argand diagrams are useful as a visualization aid, but if we restrict to that, then we lose a lot of subtle properties because all we're doing is trying to examine complex numbers as just another system of two vectors, and we lose out by doing that. We start to address some of those issues with another geometric form which is referred to as polar coordinates. So what happens with polar coordinates? We take again our standard form for a complex number, and let's suppose this complex number has some size r, say. The number in polar form we represent again as a pair, the size of the complex number, and some other object theta. And what's this other object? Well, it corresponds to the angle. We conventionally measure angles in radians, and it's the angle measured going counterclockwise from the real axis to where the two vector describing the complex number is. The two vector is drawn in what I refer to as standard position. This angle, it's sometimes referred to as the phase of the complex number, and we use this notation to describe the phase of a complex number. Yeah. And we can show the phase of a complex number, well, it's just the inverse cosine of the real part divided by the size, which is exactly the same as the inverse sine of the imaginary part divided by the size. So we look at that on a diagram. Here we have complex plane, the imaginary axis, the real axis. Here's our complex number represented as this pair. So the angle, the phase described by this vector, we start from the real axis, we rotate counterclockwise through an angle corresponding to the phase until we reach the vector we're interested in. Again, the size of that vector is just given by the first item in the coordinate pair. I'm now going to turn to a form which is very important in applications. This is called the Euler form for complex numbers. So again, we take our standard form of a complex number. It is size given by this value, and its phase is this value, theta. And in the Euler form, what we do is we describe a complex number as the size of the complex number multiplied by the exponential function raised to the power I multiplied by the phase of the complex number. And one thing that buys us is we establish quite a remarkable link between the exponential function, between the trigonometric functions, and between complex numbers. And that connection is this formula here. If we take any complex number which is written in Euler form like this, that number is exactly the same as the size of the complex number multiplied by the cosine of the phase plus I multiplied by the sine of the phase. So this is called Euler's formula. And one thing we gain from that is this relationship here. If we take any real number and we look at what the outcome of cosine of theta plus I times the sine of theta raised to that real number, what the outcome of that computation is, that's exactly the same as taking the cosine of alpha multiplied by theta plus I multiplied by the sine of alpha multiplied by theta. So this is a very useful relationship, a very powerful relationship. So we get a number of consequences from this Euler form. If we take any two complex numbers, let's say this one with size s, this one with size t, let's look at what happens when we multiply those two complex numbers. We're going to use the Euler form to do so, and so we have the Euler representation of our first complex number, the Euler representation of our second complex number. That's just standard multiplication, so we get this as the outcome. But if we look at what's happening here, the phase of this result of the multiplication, we just obtain by adding the phases of the two contributing complex numbers. So what that's telling us, if we look at what happens on our geometric position, is the phase that's a result of multiplying two complex numbers is just a result of adding the phases of each of them. Another consequence we have is that any single complex number has infinitely many different representations. Why is that? Well, the reason for that is the cosine and the sine functions are what are called periodic. The values at particular points just repeat infinitely often as we add multiples of 2 times pi onto our starting angle. So it's useful to have a single value for the phase to focus on. So we have this object called the principal value of a complex number, and that's just the angle which is the smallest one, which has this relationship between the two. So we take the angle that lies between 0 and 2 multiplied by pi, rather than any addition of 2 times pi onto our starting angle. I'm going to look now at powers of complex numbers. So I talked about some complex number operations. We know how to interpret raising one number to a particular power when both of the numbers involved are real numbers. If we turn to complex numbers, well, if our base power is a complex number, then we can extend things in what I hope will be a fairly straightforward manner. If our power is a complex number, this is a very non-trivial process. I'm going to look at the case where we're raising one number to another power, where our base number is a complex number and our power is a positive rational number. And the only case we need to consider for our powers are 1 divided by some natural number. So what happens here? We take our Euler form for a complex number, like this, the size of the complex number multiplied by e raised to the power I multiplied by the phase of the complex number. If we are computing the result of raising this number to the power 1 divided by k, then we get this. It's just a standard process. We raise the modulus to the power 1 over k, and we take the argument and we divide that by k. And what that tells us is that if we take any complex number, there are k distinct what are called principal values for the roots of that complex number, for the kth roots of that complex number. And those are all given by this expression here. So if we look at any term of this form, we raise that to the power k, then we recover our original complex number as a result. One area where this turns out to be particularly powerful is in the notion called the primitive roots of unity. So the case where our number we are raising to a power is 1 may seem rather trivial. So those correspond to the roots of the polynomial x to the power k minus 1. And we saw earlier that a polynomial of degree k has exactly k roots. So the k roots of this polynomial are what are called the k primitive roots of unity. And these all take the form as described here. The concept of primitive roots of unity, where we find that very powerfully applied, is in the notion of what's called the Fourier transform, which I'll be looking at a little bit later. This is a very powerful technique in signal processing and electronics applications. I'm going to be looking at its application in computer science as a way of developing fast multiplication algorithms. So let me just summarize what we've seen. Complex numbers, we have a wide variety of different methods that can be used to represent a given complex number. We can change between different representation methods in a fairly straightforward manner, though. There is an issue with complex numbers which I haven't discussed yet and which we haven't seen with any of the earlier number types. And that's the fact that we cannot order the complex numbers. What do I mean by that? What I mean is that we cannot have a consistent interpretation of what we mean by one complex number being smaller than another complex number. And that turns out to be a problem in particular when we look at the extensions that are needed to calculus in order for it to apply to complex valued functions. And that's something I'm going to be looking at, differential calculus in the next lecture, and then integral calculus in the next couple of lectures on the module.